In this module, we will continue with our discussion on fundamentals of quantum mechanics. We have already studied in the previous module that quantum mechanics operates through Schrödinger equation, which is the fundamental equation of quantum mechanics. One has two types of Schrödinger equation. One is time-dependent Schrödinger equation, which is basically used for non-conservative systems. And second is Schrödinger time-independent equation, which is used for conservative systems. By conservative systems, we mean the systems in which energy does not change with time. We have also studied that in quantum mechanics, if we have to study any microscopic system quantum mechanically, one basically uses 4 steps to achieve this. First step is always writing Schrödinger equation for the system under consideration. Schrödinger equation in the time independent form is h cap psi is equal to E psi, where h cap is the total energy operator. So writing Schrödinger equation basically means writing Hamiltonian explicitly. And writing Hamiltonian explicitly means writing kinetic energy operator T and potential energy operator V. Once we have written Schrödinger equation, then the next step is defining the boundary conditions of the system. By boundary conditions, we mean the restrictions which are imposed on the system. These will vary from system to system, and these need to be explicitly defined. And that constitutes step number 2. Once these 2 steps have been done, next step and perhaps the most difficult step is the solution of the Schrödinger equation. By solution of the Schrödinger equation, we mean solving h cap psi is equal to E psi in the light of the boundary conditions. And through the solution of the Schrödinger equation, one gets 2 quantities. One is the wave function psi, which is eigenfunction or state function of the system. And this is the most important parameter of the system. The entire information about the system is contained in this wave function. Therefore, it is also called storehouse of information. And the second parameter which we get through the solution of the Schrödinger equation is the total energy E. So these are the 2 quantities which we get through the solution of the Schrödinger equation. Once the solution of the Schrödinger equation has been obtained, then the next step is how to extract information out of this psi. And that can be done using eigenvalue theorem or mean value theorem. These are some of the details which we have already studied. So today we will go into the details about wave function, because this is the most important quantity in quantum mechanics. So what is wave function? What does it represent? What is called a well-behaved wave function, etc. These are the things which we are going to study. As I pointed out today, that the wave function is obtained by the solution of the Schrödinger equation. And once the solution of the Schrödinger equation is obtained, then we have wave function which would be satisfying the boundary conditions. Now, what is this wave function? That's the first question. Or how does one interpret wave function? First of all, one must remember that wave function psi is a mathematical function, and it is a function of the coordinates of the system. For example, if it is a case of particle in one-dimensional box, say along x direction, then psi will be the function of x. If the particle is moving in a three-dimensional box, then psi will be the function of x, y, and z. If it is a harmonic oscillator oscillating along x direction, it will again be the function of x. So that's very important, that one must be clear that the wave function is a function of the coordinates of the system. But now the question is, what does it represent? How one can interpret this? Actually, the interpretation of the wave function was given by Max Born in 1954, and this is called the statistical interpretation of the wave function. And this interpretation of the wave function is based on, probabilistic consideration. It is consistent with Heisenberg uncertainty principle. According to Born, wave function psi of a system is called probability amplitude, or in other words, probability amplitude is represented by the wave function. And what is the corresponding psi square? Or psi into psi star. Psi star is the complex conjugate. So if psi is imaginary, then we take its complex conjugate. Ultimate purpose is that psi square or psi into psi star, it should be a real quantity. And this was called probability density. Now, if we are able to find out psi at any point x, and then we take psi x square or psi x or psi star x, these two multiplied, then that will be the probability density at point x. This probability density is equal to probability divided by volume. Now, in the case of one-dimensional box, probability density psi x square would be equal to probability divided by volume. Volume would be along one dimension. That means a sort of volume element. So that would be dx. So you can now see that one is able to interpret psi. Psi as such has no interpretation, physical interpretation. It is the psi x square or psi x into psi star x, which is the real quantity. Now, in the case of quantum mechanics, one often talks about normalization of the wave function. Now, what does the normalization of the wave function mean? Now, you will all agree that if one calculates the probability in a small volume element dx around the point x, then it will be psi x square dx. But if the volume element is the entire length of the box, that means we take the integral from 0 to L and then psi x square dx, then this gives us the probability of finding the particle in the length of the box L. And you will agree that the total probability of finding the particle in the box should be equal to 1. So this condition must be equal to 1. And that is called normalization condition. So if the wave function satisfies this condition, then we will say that it is a normalized wave function. But suppose the wave function does not satisfy normalization condition, then we multiply it with normalization constant, and we can find out the normalization constant using the normalization condition, as you can see has been done here. Ultimately, the point which needs to be noted is that the wave function should be fully normalized, which ultimately means the total probability of finding the particle within the dimensions of the system should be equal to 1. Besides the normalization condition, the wave function at any point should satisfy few other conditions as well. First is that psi at any point should be single valued. Nowhere it should have many values. For example, here you can see the variation of a function with x, and then you can see that at a particular point x, it has 3 values. So this is not acceptable. So this is not an acceptable wave function. because it should have one value, here it is having three values. Second point which one needs to remember is that wave function psi should be continuous. If it will be continuous, then its first differential can be obtained. Not only that, it should be doubly differentiable. It means not only the wave function should be continuous, but its first differential should also be continuous so that the second differential can be obtained. So this is a second condition for the wave function, that it should be continuous and doubly differentiable. Now if you remember, for a particle in one-dimensional box, the kinetic energy is represented in terms of d2 psi by dx2. Now what is the physical significance of this? You have the wave function psi x. If you take its first differential with respect to x, as you can see it here, the first differential represents slope. And then if you take the second differential del 2 psi x upon del x2, this represents the curvature. So this has a physical significance. Here you can see we are showing three waves. These are matter waves. In one, lambda is very, very small. In another, lambda is having some intermediate value, and the top one, lambda is very large. And this you can see that wherever curvature is maximum, wavelength is minimum. You can see here. So curvature is related to wavelength. And if you remember, wavelength is related to momentum through de Broglie's equation. Therefore, one can say that curvature is directly proportional to 1 upon wavelength, or h upon lambda, or p, or kinetic energy, because the higher will be the curvature, the higher will be the kinetic energy. So this is a very important relation. And this also shows you that there are some physical concepts hidden behind the mathematics which we use in quantum mechanics. Third condition which the wave function must satisfy is, and that is that the wave function should be finite. At nowhere it should be approaching infinity, because that will be absurd. And as we have already discussed earlier, wave function is always calculated in the light of the boundary conditions, so it should satisfy boundary conditions and it should be normalized as well. Therefore, to sum up, one can say that characteristics of a well-behaved wave function are: it should be single valued, it should be continuous, it should be finite, and it should satisfy boundary conditions, and it should be normalized. And please remember, when I said continuous, continuity means doubly differentiable. That's also very, very important. Now, after having understood the significance of psi and what are the characteristics of a well-behaved wave function, the next question comes, and this was also one of the steps which we mentioned earlier, that psi is the storehouse of information. And the main purpose of quantum mechanics would be to extract the properties out of this wave function. Now, how to extract the properties out of the wave function for the system under consideration? There are normally two routes which are followed. First of all, please remember that whatsoever property we want to find out for the system and which exists, that means one which is observable, then according to quantum mechanics, there must be an operator for that. So let's take up that operator. Suppose that operator is a cap. Then we will take that operator and operate it on the wave function. And after operation, if we get a constant small a and then the wave function back, then this equation is called Eigenvalue Equation. Small a is the eigenvalue of the operator a cap. That means it is the value of the observable which that operator represents. So this is the root of eigenvalue equation. So if we want to find out any property, take its operator, operate it on psi, and if it satisfies the eigenvalue equation, then the corresponding eigenvalue is the value of the observable which that operator is representing. So simple. But suppose if eigenvalue equation is not satisfied, then in that case we use the mean value theorem. According to the mean value theorem, we get an average value or mean value of that observable, and this is given by this relation, that is, as you can see here, average value of a or a bar is psi star a cap psi d tau integral, then in the denominator we have psi star psi d tau. So if the wave function is normalized, then the denominator would be 1, and then we will have to solve on the numerator, and we will get the average value. So this is the second route, but this route is to be used when the eigenvalue equation route is not followed. Here one must keep it in mind that for every observable of a system, there exists a corresponding quantum mechanical operator. Just as you know very well that for the total energy E, there is a corresponding operator which we discussed earlier, and that is called Hamiltonian. Now we can give you a few examples which will show what does eigenvalue equation mean. Suppose there is an operator a cap equals d by dx, and suppose the wave function is sine x. Now once this operator operates on sine x, we get cos x. That means original function is not reproduced, so it is not satisfying eigenvalue equation. So the second case we take where the operator is d2 by dx2, and if it operates again on the same function, you can see it very well that here on this operation you get minus 1 as the constant value along with sine x. So here eigenvalue equation is satisfied, and the value of the eigenvalue is minus 1. So in this way you can satisfy yourself and find out whether the eigenvalue equation is satisfied or not. Let's take an example 4 which is shown here. Here operator is d by dx, but the corresponding function is an exponential function e to the power 2x. And here you can see again that again the eigenvalue equation is satisfied. The function e to the power 2x is reproduced with a constant value of 2. So this is clear. So, but one can also argue that what will be the difference between the value, eigenvalue which comes through eigenvalue equation or the average value A which comes from mean value theorem. In eigenvalue it means it is always a constant value. Even if you carry out series of measurements, its value will be more or less, will always be constant. Whereas average value represents the average of a series of measurements. So that would be basically the difference between the two. To sum up, today in this module, we have studied the importance of the wave function. We have shown that the wave function psi, which is obtained from the solution of the Schrodinger equation, is the storehouse of information of the system under consideration. We have also shown that psi must satisfy certain conditions if it is to be an acceptable wave function. In this regard, we said that psi must be single valued, it must be continuous and doubly differentiable, it must be finite, it must satisfy boundary conditions, and it should be normalized. And we discuss the physical interpretation of the meaning of normalization, which basically means that the total probability within the boundaries of the system should be equal to 1. We also discussed that psi as such has no physical significance. The real significances of psi square are psi into psi star, which is a real quantity and which represents the probability density of the system. Lastly, we also studied that once we have obtained psi, we can obtain or extract information out of this psi using either the eigenvalue theorem or the mean value theorem. In both the cases, one needs the corresponding operator of the observable for which we want to know the value. So if eigenvalue equation is satisfied, it's very clear cut and simple case. If not so, then we find the average value and that comes through mean value theorem. So these are very, very important fundamentals of quantum mechanics, and quantum mechanics revolves around these concepts.